My name is Sean Mulligan, and today I'm going to talk to you about my wind turbine, which I created for implementing in a village in Africa. And what we did during the semester was try to create several different devices for converting mechanical energy into electrical energy as efficiently and most sustainably as possible. And right now I'm going to go through exactly how we created this turbine and all the hard work we put in throughout the semester. So, starting with the base of this turbine, as you can see, there are 4 screws that have been fastened through the base to inhibit any swing or movement caused by the wind, and 2 sandbags to ensure that this base is very heavy and any wind will not disturb it in any way. Also, as we move up the base, as you come to the side here, there is a zip tie screw mechanism and a lock nut washer here to ensure that the lock nut is placed on the back, and both are tightened to ensure a solid and stationary framework. Next, there are aluminum blades here, as you can see, as you come to the front, which were custom cut, and edges were sanded to keep in mind we wanted to maximize surface area while minimizing the overall weight. So aluminum was the material of choice for that because of these properties. And as you can see, the blades get wider as you go to the top to convert as much wind to RPMs as possible, and the shape conforms to the natural flow of the wind. Also, since the blades get larger with larger and larger radius, the weight of the blades is distributed further and further away from the center, maximizing the inertia, which will keep the blades spinning, decreasing variance in voltage even when the wind varies. Finally, as you can see, there are wooden dowels which have been epoxied onto the back of the blades to reinforce the blades, ensure that they stay rigid and keep their optimal angle and framework even in high winds. As you can see, there is a this that is bolted to the frame is a standard ceiling fan frame, which has fixtures, these golden fixtures here, which have already been optimized to the optimal angle of incidence at 20 degrees. And as you come to the front, this is a propeller mechanism which has been fastened to the center of the stepper motor to generate electricity, to ensure that when these blades are spinning, so is this center rod in the stepper motor, which is generating our electricity. And custom platens here have been machined and placed to the center axle to ensure that nothing is moving except for the blades and this center rod. Finally, we hollowed out the center axle all the way to feed the wires all the way through to the back so as not to be caught by the spinning blades. And as you can come to the back, see these wires coming out. There's an 8-wire stepper motor. We tested each of the pairings using the multimeter to identify the wiring diagram, and soldered 2 pairs of the wires together to come up with 2 independent AC signals. And these AC signals, as you can come through and see on the breadboard here, there are 2 independent AC signals which have 2 rectifiers in parallel and 1 DC signal as output, and then sent through 2 capacitors also set up in parallel with the circuit, so any interruption in supply voltage will be smoothed out. Then, using the USB charging cord, we cut open and hooked up positive and negative leads to the breadboard and plugged it in. And as you can see, when the wind starts blowing, and the wind starts blowing, it begins to charge the cell phone, as indicated by the amber light here. And when you come back to the center, as you can see, when the wind is turning, it doesn't need a lot of wind to start turning. And so by optimizing the turbine frame design using my knowledge of wind physics, material properties, and resourcefulness, and finding and assembling all the mechanical parts and minimizing energy loss from the wind, we were able to maximize the RPMs yielded from the wind, and therefore could optimize the amount of electricity that could be harnessed and put into this case to charge a cell phone.